that come from this room. So now I know.
No, you're here.
But yeah, so also the thing I heard we were trying to do is a program with dentists. So like a lot of the communities have a hard time finding a dentist, but then they're training some of these kind of like nurses that are well versed in some of the basic things that dentists need to do. Like,
Yeah.
you know, fix somebody's painful tooth or something.
Right.
And then they are using the internet to stream live what the person is doing, and on the other end they'll have an actual dentist with, like, say, hearing language,
Yeah.
to guide them if there's some complication.
Technical. Yeah. Got to do what you can, right?
Yeah.
I mean, or take advantage of them. It's easier to move electrons than water or
Exactly.
fecal matter, all kinds of things, right?
Some of the good things that have come with. Actually, some of those communities have faster internet now because they had like this company that put a fiber optic cable along the western coast.
How's it going? Yep.
Looks good.
All right.
That I think ties into to Asia, and part of the deal was that they were going to connect, allow some of the communities that go by to connect to that high-speed internet. So what's your plan for lunch then? You're gonna eat lunch with
Well, there's a meeting at 3, right? I mean, I said
that meeting that's close to your hotel.
right. So I think after lunch it was to maybe with Aaron see the system, and then
I was gonna take you over to.
Yeah, have you seen the system here, or?
No, I haven't.
Okay, so yeah, you don't mind
Yeah.
checking that out, and then we can drive back. Are you going to the 3 o'clock meeting, or?
No,
because you got
my flight leaves at 5.
Yeah.
And what I was gonna do after is, if I had time, is just to meet with some of the engineers that work for Marty,
Mm-hmm.
for the state park, because I have some projects in our area that I've been reviewing. Just coordinate with them on some of the comments that I sent them.
Another one Friday. Yeah.
Well, I saw the double header. Right?
Yeah. There's a few students that I think I might have wrangled. So there's one, and then the other downstairs, they're building the steel bridge. So they said, I said you can just stay up later. They said, we were here till 1:30 last night.
Yeah, that's the big thing with the engineering schools here. They done the steel bridge competition, and they've done pretty good. I know UAF has won several awards. I don't know if they do the concrete canoe. Another one that people do. I think I see it.
Do you have a password? So we have 12 people online too.
All right.
I think we'll get going here.
Okay.
But yeah, if you want to come down, I can show you our contraption.
Yeah.
Before we take off.
No, that'd be good. Yeah.
Yeah, I like to
I think
see it.
Johnny might want to see it too.
Absolutely.
Just in pictures.
Yeah. Yeah. The next one, we said if we're doing this again, we're rebuilding it so it's not like a prototype me and the Greece students built. Make it a little more robust than that.
Oh yeah. Well, it's always room for improvement and all these things.
Yeah, or if you don't watch it, it just never ends.
Right, you need to stop somewhere.
Just reminded, I don't think I told you, if you could repeat all the questions that you get at the end.
Yep.
That way we can get it on the audio.
Yep.
And I'll ask all the online questions, so I might have a whole lot of questions.
Thank you.
Is anybody from state coming over?
One of the engineers from the state water that was going to meet this afternoon, she said she was going to try to come. Darlene.
Okay.
Darlene?
Yep.
Yeah.
I meant the people we met with this morning.
No, that's one of the reasons they asked me if I was coming to drive you. Oh,
Cheryl's here.
she's coming in. But yeah, Bill, I think had some other engagements, and then.
Well, he's short time, man. He's probably got a lot of things to check off before the end of tomorrow.
And then Dennis, I think he had some other Marty, I think. I don't know what. She might be busy.
Yeah.
Or she said she's not supposed to be working. She's on leave. But yeah, I don't know what. I know in the FedEx office they passed around the invitation, so some people might. And then Cindy Christian, you haven't met her.
Yeah.
But
She's up in
gonna be
Fairbanks?
here, yeah.
She's coming down tomorrow, you mean, or?
I think she's come from DC. Like, she must have gotten in last night. So she had enough time to schedule a trip. We need to do these like at least 2 or 3 weeks ahead of time.
I know.
So I'm gonna be there for tomorrow's meeting
Online.
Yeah.
Okay.
And Cindy, I think, will too.
Okay. Sounds good.
Yeah, yeah, so I was kind of, yeah. I feel like
So do you
I'm keeping tabs, but I'm kind
did
of.
you participate in those there's like an annual thing that EPA puts out in Cincinnati for small water systems?
Yep. Yep.
Okay.
Yeah, they had it keeps getting bigger and bigger.
Yeah.
Yeah.
I think we're gonna
I
get
just saw the
ready to go.
announcement that next one's gonna be in September.
Yeah.
I'll let Andy tell me.
He gave you a thumbs up, I think.
Okay. The delay on the side. Okay.
Thumbs up.
Get some food.
All right. We have a very small audience here in person today, but it seems like we have a bigger audience online. Last I checked, there's about 12 people online. So thank everybody for coming to our odd timed or different timed seminar series. Normally these are held on Friday, but today we have a Jay Garland from EPA to give us a talk on water reuse and lessons from Mars and early adopters on Earth. So I'm one of those early adopters. I've grown up with water reuse in the Southwest, as well as moved up to Alaska and done my own work here. So I'm excited to hear Jay's talk. For those of you online, feel free to ask questions in the comment window. I will address those to Jay after the talk. And for those of you seeking professional development hours, please go ahead and hold off on. I will get you a password by the end of this talk. My student ran off to try to figure it out. So,
Thanks, Aaron. All right. Well, I guess I will apologize beforehand for what is a very broad-ranging talk. Maybe that's good, maybe that's bad. But some of it's very broad, philosophical, talking about other planets, and some of it's very, very down to earth, talking about some near-term practical things. So, hence the title, right? I actually have got a couple talks coming up over the next month, so I have made the effort of using the same title. So I appreciate your feedback if you think you need a new one. There's a lot of people involved in this work. I'm really just kind of the face on a lot of this stuff. There's a lot of people inside EPA Office of Research and Development. That's who I work for. Contractors that support us. The third line is the National Blue Ribbon Commission on on-site non-potable reuse. Paula Kehoe is the individual from the University of San Francisco, not university, but the city of San Francisco that leads that effort. And that's a very important part of this work. And then a number of other people from the region, and EPA Region 9, Colorado State University, other colleagues at universities. So, all right, so my extraterrestrial background. These pictures here, I don't know, you have to be a really sci-fi geek to know what this picture's from. But that's from a movie from the 70s called Silent Running. And it was about a guy who was, they were transporting biomes from the Earth through space and preserving them in these kind of terrariums going through space. That was the movie. And then these are artist rendition of a Mars base, hence the red color, and a lunar base. And this is what I spent about 25 years of my life doing from graduate school to about 8 years ago. Now, these are systems that we have not done yet. When we went to the moon, we didn't have those kind of things with us. More recently, this is pictures from a movie called The Martian. I don't know if you saw The Martian, where Matt Damon, as a stranded astronaut, was forced to grow potatoes on not his own poop, but the fecal material of his colleagues who had left him behind. And that's actually what I did specifically, was working on bioregenerative life support systems for NASA. We looked at what kind of productivity of plants you get out of a square meter, both in terms of the food production, the atmospheric regeneration, the oxygen, the water production.
Was he right?
We definitely worked on potatoes because it has the highest harvest index of any of the agronomic crops, right? 80% of that plant is edible. So if you're trying to grow something to eat, you want something that produces a lot of food, and potato is the best harvest index. So yeah. I like to joke too that I like to show this picture because it's the one thing I have in common with Matt Damon. Right? I grew potatoes on my own poop. So the other side of this too, though, the real reason why I show this is two reasons. Why this background, I think the best things that it gave me. Number one was this perception that, we had not done this. I spent the early part of my career working on something that nobody had ever done, and we still haven't done. So there weren't any limits in what we should be doing. And this quote is from a book called The Ghost Map by Stephen Johnson. This is actually a book about the discovery of the mechanisms of cholera transmission in London. And the idea that before we understood that it was a waterborne transmission, people thought it was the air and bad vapors. So this quote is, the river of intellectual progress is not, defined purely by the steady flow of new ideas. We're kind of blocked sometimes because of what we can't see, right? We have certain biases and misperceptions, and then sometimes those clear up and we get a whole new view on things. And that's why working on this project was so good, because there was nobody laying some block in front of us saying, well, this is the way you should do this. The other way to simplify this is the Sufis have a saying that traveling polishes the mirror of the mind. When you get a different perspective, you actually see yourself more clearly. This picture of the Earth rise over the moon, going back to the NASA link, that some people would say was the best part of the Apollo program, of this change of perception of having people outside the planet looking back on it and saying, geez, look at that fragile blue planet in the blackness of space. The second thing that this perception, I think, is important, that took away from it, is this idea that, if we could learn how to live on an extraterrestrial planet where all the things we're producing are recycled and sustaining ourselves, if we could do that on Earth, we would get rid of a lot of the problems that we have, because we tend to develop our systems based on extraction and disposal. One-way kind of flows. We do not design regenerative systems. This quote is, is this kind of the Rosetta Stone? If we could learn how to develop systems, the moon or Mars doesn't have any ecosystem services. So we have to generate all of our ecosystem services in a regenerative fashion on these planets. So this idea of using the intelligence of natural systems to inform our own human design. I don't know if you're familiar with this book by Michael McDonough and Brandgart called Cradle to Cradle. This idea that this concept is, we got to get beyond the idea of feeling good about doing less bad, about recycling things. Because then we're just trying to say, okay, we're going to spend extra energy and time and effort making something that's lower quality than we kind of want, but it's better than throwing it out, right? So if we had designed it originally in the first place with this idea of regeneration, then it would be much more sustainable. And their idea is, well, natural systems do this. So what are some of the rules? Well, waste equals food in natural systems. There aren't waste products in natural systems. Most natural systems are based on using current solar income, be it mostly solar radiation, but also maybe natural winds. And celebrating diversity in this sense about all natural systems aren't the same. They adapt specific solutions for the local environment. So this actually, this whole concept, this book, an intern gave it to me my last year when I was working with NASA, and she said, what you guys are doing, this is it, and it actually made me want to come back to Earth. So I came back to Earth to work for the EPA. I said, I'm going to come back to the Earth and work on these kind of approaches and save the planet. I'm going to save the world. I'm going to change the world. And that's what I did 8 years ago. I told my wife, let's move from Florida to Ohio. We're still married. So it's another way of kind of viewing this is, no, she didn't come with me. She's from Puerto Rico, so she doesn't like cold weather. But anyway, different story. This idea of another way of looking at this is you know, there is biomimicry. You know, there's people who design specific functions, like Michael Phelps's swimsuit based on shark skin. You know, the design elements on shark skin that you can apply to how to more aerodynamically pass through water. Hydrodynamically pass through water, the fin of a whale, the carapace of a beetle for condensation. I mean, this is biomimicry. If you're interested in this, all Biomimicry 3.8 by Janine Benyus is really good overview of this. And that's clearly one thing that's, you know, this is design solutions from nature. But, you know, another way to kind of next step on that is, well, let's think about beyond individual organisms, but into ecosystems. And how do ecosystems work? This waste equals food, this idea of industrial ecology. This is the kind of classic example from Kalundborg, Denmark, where they designed all these linkages between different industries there. And that's certainly the way ecosystems work. That would be an advancement for increasing efficiency. But then even one step beyond that is, how do ecosystems really work? I mean, how do you apply natural sunlight out in the environment and you get these self-generating, self-organizing systems develop? You know, I mean, one way to view that is, you know, if socio-ecological systems are self-organizing, they respond to the environment, there's multiple steady states, there tends to be these local minimum. That's where the system's state tends to be. But what we tend to do is we tend to push our systems up to some edge. And I use edge here as a lawn in a suburban area, right? We want to maintain a green lawn. That's the system state that we want. And what do we do to get there? We apply a lot of exogenous energy. In this case, it's sometimes your crazy neighbor who's out there pulling individual weeds, but it's application of fertilizer, other kinds of things, lawn mowing, right? So we spend energy to get to this non-steady state. Or should we design for the local minimum, right? Actually, in this case, this is in Florida, there's some people use peanuts, natural peanut perennial, instead of that kind of grass. This can establish and be a low input system, right? So, you know, so what is the local minimum without exogenous energy? If you look at natural systems, you shine light on a coral reef, you get these kind of very vibrant, productive systems develop. What happens to our systems in the absence of exogenous energy? These are pictures from Detroit, right? So what's happened to Detroit over the last couple of decades when we removed all the wealth and other energy that was flowing through that? The systems decay. All right, so this is, you guys are thinking, this guy is crazy. He's talking about all this stuff. And I don't know how to do this, all right? I mean, how do we really design our systems, our human systems, where we wouldn't need all this exogenous energy? I don't know how to do it, and it's certainly beyond my current job description, okay? This is not what the EPA is paying me to do. But there are some of the elements of this. Let's go back to the simple thing, a relatively simple rule of waste equals food. And EPA works a lot on water systems. And there's two ways to view this. You can view water as waste that you got to deal with, or you could view it as a resource to be utilized. So a building, you know, the rainwater falls on the roof of it. Stormwater collects at grade around it. There can be drainage or groundwater accumulating around the foundation. You generate wastewater, either gray water from washers, bathtubs, showers, bathroom sinks, or actual black water from the toilets. So all these wastes are generated, and even AC condensate is generated. So buildings, they produce all these things that you have to deal with. But the design rule here is waste equals food. They produce water, so why not use it? Not figure out, design how to get rid of it, but design how to reuse it. So, and that's what the rest of the talk really is about. This kind of relatively focused approach for regenerative design. Not that I haven't forgot about trying to completely change the world, but like one step at a time, right? Examples of this, there's a lot of people doing this. This is the Solaire building in New York City. They've been processing 25,000 gallons per day of wastewater, where they treat it with a membrane bioreactor in the basement, and they use it for toilet flushing and cooling irrigation. They've been doing this for over a decade now. And why are they doing that? You say New York City, they're not in the arid Southwest. It's not like they don't need water. They need the water, but they were actually reducing their wastewater flow and reducing the tax on their sewage because they have combined sewer overflows, and there was heavy pressure to reduce sewer flows in New York City. San Francisco, I mentioned them, the public utilities headquarters. They designed this, both a rainwater harvesting system and a wetland treatment system to collect the wastewater. In this case, all the wastewater from the toilets and the sinks in the building, 5,000 gallons per day or 25,000 gallon overall cistern. And they have a treatment system which includes a natural system outside. This is what the pictures are. So when you walk up the building, you see this tidal flow system that is part of the reuse. Also in San Francisco, because San Francisco has now required any new building over 250,000 square foot to put in some form of non-reuse. This is the Fremont building. It's kind of business downstairs and high-end apartments on the top, and they're in gray water and reusing it for toilet, through membrane bioreactor system for toilet flushing mainly. And their main drivers was they want to have a building where they could become LEED. Everybody familiar with LEED, like it's kind of like the Green Building Council, and they give you credits, and then you can certify that your building is gold, silver, or even platinum level. So it's kind of like an award system. Salesforce Tower, which is the second tallest building west of the Mississippi in San Francisco, a 1.6 million square foot office building. They're processing 30 gallons per day of black water, again, for toilet flushing, for mainly the same reasons for this certification. Haslow on the 8th in Portland, Oregon, they've designed this system to process up to 60,000 gallons of wastewater per day, low energy treatment. These are part of the bioreactors or holding tanks there. They light them up at night, so they look kind of pink, right? So it's aesthetically pleasing from that design, but then also it's below grade and a lot of green vegetation-based treatment here. So a lot of people are doing this. And back in 2014, as this was emerging, there was a group of utilities and public health agencies across the country that got together in San Francisco. And again, this map shows you that it's not just a Western thing. It's from across the country, interested in trying to catalyze the adoption of safe adoption of these systems. And the two things that came out of this meeting, what they said is needed is, number one, local management programs. Somebody needs to develop programs to be able to effectively define and monitor these systems and ensure their safe operation. And secondly, somebody needs to tell them what the water quality parameters and monitoring are needed. What should the treatment be? And so we were involved in that, and we developed a research program around those questions, really. All right, so this graph here kind of shows. All right, someone's going to tell me you're not finding new water, right? There isn't new water. New water comes in on the planet on meteorites. Okay, we probably got most all the water we're ever going to have. We're not finding new water, but finding new sources and alternative sources of water. In this case, rainwater, gray water, black water, storm water, all those things I mentioned, treat it for non-potable reuse. The three main questions that we've been looking at is, how do you define the acceptable treatment? How do you monitor treatment performance? And this third question, which I'm going to talk about briefly, is, does it make sense to do this? All right, now this question here is very complicated because there's lots of different drivers for why it makes sense or not. All right, so the rest of the talk is going to be, I'm going to talk briefly about this and then these two. So in terms of the drivers for this, clearly water scarcity, finding more water, that's certainly what's driving a lot of it out west. But there's also this perception that it's more efficient, that if you treated the water only as much as you needed for some fit for purpose use, right? Don't treat why are you treating water to potable standards, right? Wouldn't it make sense to have different, and why use the same treatment for everything? Also, if you treated the water closer to the source, you could provide construction of recycled water pipelines, and there's a lot of purple pipes in areas of the country where you're taking it from the centralized plant, it's drainage there, then it's collected, it's treated, then you pipe it out. All right, so what about just eliminating that whole network of purple pipes? And if by doing that, can you defer capital costs of large-scale infrastructure? If you're becoming more efficient by reusing and reducing your local water footprint in a building by 50%, let's say, because you're not requiring more potable water for the flush toilets, then you don't need to build a new drinking water plant. The other rationale was you reduce pollution and loading to the sewers and the water bodies. And particularly this question of sewers I mentioned in the Solera building in New York City, they did it because they were getting taxed for the sewer flow. So by reducing, if you're recycling your wastewater, you're cutting your wastewater flow at least in half. And also, and this is again, it's kind of a perception, and we'll see whether how it holds out, but does this increase your resiliency and adaptability of your water and wastewater because you have multiple systems? You're not relying on one centralized treatment and either drinking water or wastewater system. And also, there's interest in, especially in urban environments, using that water to create green spaces and meeting and exceeding green buildings goals, like I mentioned, which was driving some of the LEED certification. Now, these are all the drivers that this group developed. Since that group met and I developed this slide, I met you all from Alaska, and you guys have a whole nother driver, really, which is sanitation. There are rural areas here where you're trying to look at reuse because the current system is not, there are sanitation risks and health risks associated with poor kind of infrastructure, mainly on the wastewater side. So you want to recycle the water to allow for more water available for hand washing and hopefully deal with some of the transport and handling of the solid waste. All right. So I mentioned the first question, does this make sense to do? So, there's a lot of drivers there, and it may make sense for you to do it for a variety of reasons. But one of the other things that we've been doing is asking the question from the perspective of kind of cumulative impacts of, let's say you're going to do it at a building level. Are you actually saving energy, or are you spending more energy by doing that treatment locally? So what we've done is we took some scenarios, looked at a 19-story building, 20,000 square foot area, mixed use, got 1,000 people in it, and they produce 25,000 gallons per day of wastewater. And we wanted to say, okay, if you're going to treat that, you can treat it a variety of different ways. You can treat the wastewater, the overall combined flow, or the source separated gray water flow from that building. And then you could treat it with aerobic MBRs. I know you guys are engineers. I think most of you are. You know what an aerobic MBR is. It's a membrane-based bioreactor using biological treatment to degrade some of the organics, or hopefully most of the organics in it. Then also has a filtration of the effluent. It allows it for small footprint systems, and those are the ones I mentioned during these buildings. They're actually in the basement processing up to 20, 30,000 gallons per day. And they're commercially available. The problem with these is, though, that you're aerating them. So you're supplying oxygen, you're mixing. That is an energy consumption. There are emerging anaerobic systems, same membrane-based systems, same small footprint, but you're not aerating, so you're reducing your energy costs by not aerating, and you're generating biogas from those, and you can use that locally for energy. There also are people, I mentioned the vertical flow. There are a number of kind of wetland-based systems. There's actually a high performance, like a vertical flow wetland system that the Israelis have developed that's small, compact print, and we looked at that. And also the idea of looking at heat recovery from this locally collected water. Because as you know, especially the gray water, can you collect that heat there? So this would be, the anaerobic MBR would be chemical energy recovered from that wastewater. Can you also recover it, just from heat transfer and use that locally? So my budget's not that big, so we didn't do like all these things in reality. We used life cycle assessment. So we kind of modeled the performance of these different systems to look at the cumulative impact. right? So this graph shows the cumulative energy use for these different options. So just a little bit of background on this slide. I know there's a lot on it, but here these two bars are for the aerobic MBR, wastewater, gray water. This is for the anaerobic MBR, wastewater, gray water, and whether you continuously sparge or intermittently sparge. And that means these membrane systems, you have to clean the membranes. So you have to sparge, use the gas to kind of sparge them. You can do it either continuously, or there are new systems to try to do it intermittently to reduce the amount of energy you're using. Here's the vertical recirculating vertical flow wetland, and here's the aerobic MBR coupled to thermal energy recovery. Yes. All right, so this wetland really was it. There, I showed that picture earlier where there's some plant-based element to it, and that was the one that was outside at the San Francisco building. This design, though, this vertical flow wetland, it's almost like a very small-scale hydroponic system, where the water is circulated through this soilless system. So you're using the roots of the plants basically to do some of the degradation. So it's compact, and you can grow whatever plants you want into there, that you can work into this kind of vertical flow. Just means it's kind of oriented vertically. So for a building application too, you can kind of have a larger plant area for a smaller surface area footprint. And the reason why we picked that one was I'm going to talk about this. We do a lot of work on looking at the removal of pathogens in these systems, and for that one, we actually there were numbers on pathogen removal for that one, as opposed to some of the other ones. But this graph, all right, so I know I was going to talk about this briefly, and I'm rambling on, but the bars that you see there are the the energy cost for doing this system. The part of the bar graph that's above zero are the cost of operating that system locally, the cost of operating an aerobic MBR for treating wastewater, the combined wastewater or gray water. The stuff that's below zero is the avoided cost, which means that if I'm treating this water locally and flushing toilets, what I'm avoiding is supplying that building with drinking water. And there's a cost to that, right? So that's what the purple bar is. Does that make sense? So it's cost. I'm not saying that, you're going to cost something locally, but at a community level, what's the cumulative energy use for this option? So you see there's purple bars that are below zero for all of them because it's avoiding drinking water in all of them. The little hatched bars there on the anaerobic MBRs, that's the energy that you're actually recovering via the biogas that you're harvesting and using locally, right? You can harvest it and burn it. And so you see it in the anaerobic MBRs, you don't see it in the aerobic MBRs because the aerobic is not producing any biogas, and neither is the recirculating vertical flow wetland. And then in this case, you can also gain energy by this thermal recovery. So you heat transfer from that hotter water. So what this shows you, if you notice the little white dots on each one of the bars, if that white dot is above zero, that means that there's more cumulative energy use for employing that system locally than not. But if it's below zero, it means that the net system costs are negative. Not at the building level, but at the community level. So in this case, it shows you that aerobic MBR, it trades fairly well. It's actually net zero or slightly zero cumulative energy use. Anaerobic MBRs is for continuously sparging because there's more energy in that continuous sparging. It's above zero and it's slightly below zero. It's more so if you optimize your anaerobic system, it's below zero. The recirculating vertical flow wetland, because there's a lot of recirculation and the cost of that pumping, it's actually kind of neutral or slightly above. And then the thermal. If you're replacing electrical heating of your hot water locally, there's a vast amount of savings. That bar is the lowest. Now, if you're replacing natural gas heat from a life cycle perspective, from a cumulative energy use, replacing gas with local energy, because these heat transfers, they use some energy, electrical energy. That's actually a net. That natural gas is always more efficient than electrical energy. But if you're trying to replace electrical energy, it's good. So bottom line. Let's see. Net benefits if you account for avoided drinking water. So if you're really trying to make decisions about this at city levels, it does seem to make sense if you're thinking about it from a community level. The recovery of the thermal energy can provide significant improvements. The system level benefits of recovering chemical energy via this anaerobic membrane bioreactor, they're actually diminished because some of the cost is partly because you have all this reduced nitrogen that you have to kind of pull out, and the costs with doing that are the largest part of that positive air bar. So anyway, this isn't relevant to remote villages in Alaska, but it is for some of the people for these urban applications. Bottom line is that the question is, does it make sense? Well, it might make sense for a lot of drivers, and it does make sense from a cumulative energy use from a perspective of the city. So this next question of how do you define treatment is probably the most thing you're probably most interested in, related to the work we're doing here in Alaska. The problem as it exists now is that there are standards out there. If you're going to reuse gray water, the flush toilets, you can go out there and different states have different rules to say, well, if you want to do that, you have to treat the BOD, TSS, turbidity, you have various water quality parameters. And let's look here, particularly on the coliform levels. You know, your effluent needs to be at below this level of fecal indicator bacteria. That's what coliform or E. coli are. And, you know, you start off fairly high, like 10 to the 7th or 10 to the 5th, this range. And I show that just because we're talking about microbiology, and I'm going to talk about log removal credits, and those are very high. Microbes occur logarithmically, so you start talking about removal of microbes, you're talking about levels, right? So there's lots of standards out there, but does that mean that you know, some don't have any rules at all, and they have different rules? Why would the rules be different in one state versus another? Right? Well, there's a lot of reasons, but does it make sense for there to be different rules? Not really. Gray water isn't necessarily different in Georgia versus California, for example. NSF, the National Sanitation Foundation, they've actually developed a nationwide common approach to this. So that eliminates this idea that there's variability. So here are their standards, and you got to meet, if you want a class R, which is flows of gray water system less than 400 versus greater than 1500, class C, they have very standard nationwide levels of this. So that's good. There's standardization. But the key question is, what do those levels mean in terms of risk? Right? What does that level of E. coli mean in terms of risk? It means you know, what does it mean? It just means, well, you think the water's good. That's that value. Why is that? Where did that value come from? And it didn't come from someone saying, okay, I'm going to reuse this gray water in a house. I want to know how many, what do I want to know? What's E. coli? E. coli is an indicator of fecal pollution. It's not any pathogen itself. So you really need to think about it from what the risk of infection is. And that really doesn't tell you anything about risk. So how do you approach that? Well, go back to NASA. Back when NASA was asking the question, if astronauts are going to eat food in space, what's the risk from them eating that food? And what they did was they developed this hazard assessment critical control point of really related to food safety. But the idea was a very structured engineering approach to defining risk. And that approach was originally, really came from the munitions industry, because they wanted to have very good control over how you minimize risk associated with explosions in munitions plants. So that was transferred to NASA and food, and it became very popular in the food industry, this HACCP. All food packaging production facilities have this HACCP plan. Where are the hazards, and where are my critical control points for controlling and reducing that hazard? And that then developed into what I'm going to talk about is the quantitative microbial risk assessment approach. The first step to QMRA, and the next slide details that further, but the first step to any risk assessment is you have to define what your acceptable risk is. And this is not an easy question. What risk are you willing to accept in the population for if you're going to do a certain thing? In the water world, in at least in EPA's world, there tends to be two different rough estimates of acceptable risk. Not rough estimates, but two ranges of acceptable risk. One is 10 to the minus fourth infections per person per year. 10 to the minus fourth. That means that one person per year, you know, in 10,000 versus 1 in 100. Right, those are the 10 to the minus second is 1 in 100. And the World Health Organization, they've applied these risk-based targets for wastewater reuse in agriculture. And so has the state of California for direct potable reuse of wastewater, taking wastewater to drinking water. So the question is, why is there a range? Well, it's the 10 to the minus second infections per person per year. That's what the rules are for recreational water use. So we have guidelines for E. coli levels in swimming areas, and we close beaches if we think the E. coli levels are above a certain level, and that level is equated to about 10 to the minus second infections. 1 in 100 people getting infected. If it's higher levels than that, they've done the models indicate that that's when you need to close the beach. So if you live in places like Cleveland and you're swimming in the beach, you might, you know, if you look around you and there's more than 100 people swimming in the beach, you know, you might be that one. Yeah, yeah. Epidemiology. Okay, so the question was, like, say in China where they're applying sewage to fields, you know, the question is what the actual level of infection is. I think is what.
Well, it seems like we could learn from them. I mean, that's pretty drastic.
Yeah, the problem with epidemiological studies, I mentioned here that for the 10 to the minus second infections per person per year rec water, there were epi studies done where you actually determine how many people are getting infected when levels are at this, you know, the indicator levels are this. But that's hard to do, and it's really hard for 10 to the minus 1 in 10,000 people. What's your sample size for that? So it's really hard to get data on the actual level of infections. Because you'll get pushback on this a lot when we're recycling water, like in the gray water recycling world in buildings. There's people say, well, you know, we've been doing this forever. Nobody's gotten sick. Like one argument was Solaire building, right? They've been recycling water for 15 years. Nobody's getting sick. Do you really know? Do you really know? How many people are living in the building? I don't know, 1,000? Was it 1,000? So, okay, was one person per? Have you actually increased the risk of infection above that? Now, you might then counter and say, well, do you really care? That means you ought to have very much lower standards, right? Your acceptable level of risk should be lower. And that is a question that it should be debated. But again, QMRA, this whole risk-based approach, starts with saying, okay, what is your acceptable level of risk? And you can model for different levels of risk. All right, so in QMRA, the basic idea is that you, in a systematic way, go through identifying, okay, what's the density of pathogens in whatever water I'm talking about? What's the density of pathogens? Not the indicator, but the pathogens. How much volume of that water then am I being exposed to? Then what do I understand about the dose response of that pathogen in humans? Then you have a predicted risk, right? Then you actually know what the risk of infection is in the population. Then you say, okay, what's my tolerable or acceptable level of risk? And the difference between the predicted and the tolerable is this log reduction target. This is how you need to treat the water to get to an acceptable level of risk. But it depends on you quantifying what's the density of pathogens, what volume of water we're being exposed to, and what do I understand about the dose response. It's that simple. It really is pretty straightforward. And that's it. So what we've done is apply that approach to a number of different source waters, like I've mentioned. It could be roof collected, any source water, right? You look at those up there, but there could be additional ones. And then there are different end uses that can range from non-potable to potable use. And the more in this direction, you're going to have higher levels of treatment. And what we've done is developed a matrix of log reduction targets to define what I would say this fit for purpose use is. Then you have some basic framework for saying, okay, what do my systems need to do? Right? And that's what we're talking about doing with your all systems, right? And it's not, despite some of the references I've used earlier, this is not rocket science, right? It's pretty straightforward.
The trick is probably getting some of that data.
The trick is that you're making a lot of assumptions. You have to make a lot of assumptions because you don't know all the data. And I definitely will readily admit that. But the idea is you have a structured framework. You know what all your assumptions are, and you can say, this is the biggest uncertainty, and that's what I need to improve about my understanding to get better estimates. But it's all there. You're not just pulling some number from some previous, estimate of what 50, 500, 2.2. And you need to think about, first thing you need to think about is what are the pathogens of concern? Typically in wastewater, in fecally contained, there's viruses, bacteria, and parasites of concern for, particularly for wastewaters, be it gray water, because gray water is contaminated with fecal matter. It's not as much fecal matter as black water, but it's still got fecal matter in there. And these specific examples here are norovirus, adenovirus, rotavirus, Campylobacter salmonella, Cryptosporidium giardia. Those are the most common reference pathogens used for enteric disease in wastewater. So those are the ones you need to develop log reduction targets for. And they're typically by these classes of virus, bacteria, and parasites. Usually you try to pick the one that you think is going to be the greatest, maybe at the highest concentration or has the lowest exposure dose response. No. I mean, that would be there are other bacteria too. And if we're talking about different exposure pathways, of maybe you're worried about skin exposures, maybe you're worried about certain kinds of staphylococcus or things, right? So, or Pseudomonas aeruginosa. But these are the common ones for wastewater exposures, because toxo isn't as, if you're meeting a standard to remove parasites, then you're probably going to meet the toxo rule or whatever the toxo risk, right? And the reason why these are classified this way is that, the treatment systems tend to perform differently by these, different sizes, different susceptibilities to the treatment technologies. So, but how do you estimate? Let's go back to that model. First thing was, what's the pathogens? What's the concentrations of pathogens in? Well, let me step back one step right here. This is enteric pathogens. And that's why you get a lot of E. coli used or fecal indicators used, right? Because the fecal load is going to be, these things are going to be the level of fecal contamination is going to impact the level of these fecal or fecal-borne pathogens. But if you're collecting rainwater and reusing it, would you develop a log reduction target based on a fecal indicator? Human fecal indicator? Yeah, because what I joke with people is like, okay, if you're worried about human feces on your roof, you probably need to take care of a lot of other things before you start thinking about reusing water in your building, right? So you really need the first step is framing the problem and what the reference pathogens of interest should be. And going back to that graph of all those different source waters, the kinds of reference pathogens are going to depend on what type of source water, alternative source water you're thinking about. But you want to know for a given water, you want to know what the pathogen concentration. When we did our initial evaluation of rainwater, stormwater, black water, gray water, we went out in the literature and said, okay, are there at least 15 studies using conventional methods that actually we're able to have detection above the limits of the methods. If there were enough observations, we could characterize the density that way. If there wasn't, we had to model it. And we had to model all of them because there's a lack of data for these kind of systems. Not on the indicator levels, but on the actual pathogen levels. So what we did, one thing we did was for estimating fecal contamination in black water and gray water, we developed a new model that there was a lot of data out there on fecal loads in gray water and in black water. But what we don't know is what the pathogen levels are in that wastewater. And this depends on how many people in your population, how many people are infected in your population, and then what the pathogen shedding duration is around that particular disease. So we modeled all of that so we could estimate what the fecal load is, but beyond the fecal load, we know, okay, there's this many feces, and we know there's an estimate of what the number of pathogens are, because there's the number of infections happening, and that gives us the actual pathogen concentration. So we modeled it that way. So the first thing you say, okay, you're making a lot of assumptions there, Jay. How accurate is that model? So one of the first things we want to do is we went out and looked at one of these locally collected wastewaters. This is from the San Francisco Public Utility Commission building, not after treatment, but before treatment. So this is just what is generated in that building. The values that you see here, this is the solid line and the error bars are this is the mean predicted concentration of norovirus in that water using that epidemiological approach that I mentioned. And here are the ranges, the 95 and 5%, 95%, 25%, 75% probabilities around that line. And then these data are the actual measured levels of norovirus in that building's wastewater. So pretty good correlation between the modeled and the predicted. Again, it's logarithmic, right? Logarithmic scale, but it does bounce around what our average estimate is. The other part of the model is the exposure volumes. What is the amount of volume that you're being exposed to? Well, when you flush the toilet, there's a certain volume that you're going to ingest. There's aerosolization from toilet flushing. There's aerosolization from clothes washing. And here's the volume. Very, very small volumes, 0.00001 liters. So fraction of a milliliter. That's what you're exposed to. And you could estimate that there should be improved estimates for those too. But then to get the exposure volume, that's how much happens. That's what you get exposed to every day of the year, because we're assuming that people are flushing their toilet. This is back in the lower 48. You're flushing the toilet every day. For clothes washing, you're doing that not every day. So it's not 365 days a year, but it's 100 days out of the year. And then there's also estimates of what we think accidental ingestion would be from cross connections in the system. And that can happen, especially when you start installing these in a building. You've got reused water, and you've got your the drinking water lines. So we estimated that as, and this was a complete swag, 2 liters per day. That 2 liters is what you're going to get by drinking. That's the volume you drink per day. And that happens 1 day out of the year in 10% of the population.
One cross connection.
One cross connection that happened. It happened for 1 day of the year in 10% of the population that is reusing. And I will say that we did look at this question in more detail. We've looked at it and looked at a range of estimates on this and what the impact on the model. And to be answered, it's actually not that much. So now you can also model it if, again, you could do direct potable reuse. So if you're drinking it, you're getting 2 liters per day, 365 days a year, and 100% you're assuming that everybody's drinking the water. So that's how you do the exposure volume. And so then you end up with, by solving, here's what you end up with in terms of getting this big list of log reduction targets for quantitative microbial risk assessments. And so I think for the sake of time right now, we don't kind of blow through that. But basically, this matrix, in this case for viruses, protozoan, bacteria, what we've got here is we're using domestic wastewater and black water gray water, storm water, roof runoff. All right. So, and we have gone through and looked at, for your application, specifically what the LRTs would be for bathing in recycled water. Because this data here was only for flushing toilets. If you start to bathe in it, you're not drinking it, your exposure volume is going to be different. What it is, hard to know. But we looked at studies involving people who swim and how much they ingest when they swim. I know you're not swimming in your toilet, in your bath water, but there's some estimates of what the ingestion could be. So we've used those estimates to come up with kind of revised numbers, which are approximately 1.5 log greater than the traditional non-potable use. So it's slightly higher, but it's about 3 log lower than if you're going to do direct potable reuse. Right, so the ingestion volume is higher than that small amount of aerosolization you're getting, but it's much less than full drinking. All right, so real quickly, let's talk about the third challenge of, let's say let's say you believe me that this is a decent way to go about applying these models to define this is what your treatment systems needs to be. So that means you're going to get a treatment system and you say, okay, this treatment train removes, we're going to give it each one of the elements of the treatment train, log removal credits, and together it's going to meet the log reduction target for this particular wastewater for this reuse. All right, so you design a system to do that. And then you got to say, okay, how do you monitor that treatment's actually working continuously, which is a big deal. This Blue Ribbon Commission that I'm part of, what they've estimated, right? So you've designed your system to meet those risk-based performance targets. You got multiple barriers with sufficient log reductions. How do you verify it? Well, one thing is you'd say, okay, do routine monitoring of some indicator organism. Well, that doesn't really provide you real-time risk-based information. We've already talked about this. It's not risk-based, and it's also not real-time, right? If you're going to tell somebody to go pull a sample, go do a fecal indicator, and what are they going to do? They're going to push back in the drinking water world. How often do they do that? As little as possible is the answer, right?
Monthly is the most frequent one.
Right. So that means
It takes 2 or 3 days to get to your lab.
right.
And then
So 99.99% of the time, you're not protecting public health, right? So wouldn't it be better to use some online approach that's really telling you that, okay, I've designed a system to meet this log reduction, and I've also verified that these are the critical control points in my system that I can monitor to tell me that it's meeting its performance. If that's the case, then you're doing it all the time. Now, so operational monitoring, ongoing verification of system performance using continuous observations with some surrogate parameter that's correlated with log reduction. That's the real key here. So for any new system like the system you guys are developing, once you we've kind of gone through the numbers. I mean, your system's going to meet the log reduction target of that, right? It meets it. So the question then is, okay, based on your system, what are the appropriate surrogates to say this is what you want to monitor, as opposed to relying on some grab sample water quality indicator? Because you certainly, you guys, in 5 minutes, you don't want to go through the whole. I got about 10 slides on microbiological analysis, and what we're looking at is alternative approaches to monitoring. This is, once you start up and commission, you need to validate your system is actually doing it. And then you want to maybe do controls for out of specs. Let's say your system has been disrupted, it's been shut down and turned back on. You are going to want to say, okay, I'm going to validate that my system still is having those log reduction targets. And then you would actually want to measure removal before and after of some target and say, yeah, my log removal is appropriate. But then most of the time you want to rely on this continuous operation. And one of the things we've been working on a lot is on this side, if you are going to use something, if you're going to measure something before and after treatment, based on those log reduction targets that I mentioned, what are those targets? What should those targets be? And they're not the typical indicators. Well, they're not pathogens, because the pathogens, there's hundreds of different pathogens. They occur sporadically, right? So you may not see it in your effluent, but that doesn't mean your system's operating effectively. It just means nobody's sick right then, right? And it can be expensive, and you get a lot of negative results because some of these the dose response is very low. So a few particles can be a problem, and it's hard to measure a few cells. The typical biological surrogates that represent pathogens, like the fecal indicators, they tend to be too dilute, is what we found. And you could try to spike with some other surrogates. Well, that means you're going to grow up some virus or some bacteria, and then you're going to spike it into your system and look at its removal. That can be a challenge, especially for these larger systems, some of the ones I mentioned that are hundreds, tens of thousands of gallons. So what we're looking at right now is endogenous microbes, things that are there in the wastewater, not the pathogens, not the fecal indicators, things that are at very high levels that you can measure before and after treatment. And there's a whole rich area of more possibilities there, because we can quantify a lot of organisms that are there. And I'll close here with this. This is some work that we did with gray water. And here are bars of all these typical indicators: E. coli, Bacteroides, which is another marker for, and there's a human-specific Bacteroides and Enterococci. These are all indicators of pollution. Some of them are more human-specific than non. And here are what the levels were in gray water. And then we also, with these new genomic capabilities, we looked at a whole bunch of other stuff. Pseudomonas, Corynebacteria, Propionibacteria, Staphylococcus. These are skin things that are associated with the skin of humans. They're much higher level, right? Consistently. And that black line there is at about 5 logs, because that's the level we assume that if you're going to meet the 10 to the minus 4th acceptable risk, if you're going to measure something before and after treatment, you need to have it at least that level, because you want to be able to see it in the effluent too, at a low level, but you want to see it before and after treatment, say my system is removing that amount of bacteria. Without having to spike something, if you look at the typical fecal indicators, they're not high enough. But some of these other alternative markers could be. And those are human-associated skin bacteria, right? So they may be better. They may be better surrogates. We did a deeper profile. This heat map is of deep sequencing of the gray water microbiome. And in the laundry water that we sampled directly out of a laundry machine, you saw a lot of human-associated bacteria in that. But when we looked at these are shower waters that this may sound familiar to you. We sampled it from a dormitory recycling system in Colorado State University. What we found there was we didn't see the human-associated bacteria much. We saw it some of the time, but what we saw mostly were these other organisms that were things that we know are associated with waste treatment plants, kind of low oxygen, microaerophilic organisms, things that are associated not with the humans, but with the pipes. So by the time we were sampling the wastewater, it had flowed through the drain, through the pipe. So you're sampling the infrastructure of the system. So maybe those are the better targets to look at, right? Because they're at higher concentrations than even the human associated in the real gray water that you're going to treat. Because this is what you're treating, not this. Now you can say, well, that means the stuff's already gone. Yeah, well, it is being attenuated, right? So, but you're going to get a log removal credit, some log removal credit for your pipes? Maybe. So anyway, and then there's viruses, and this is we've done the same thing with viruses. We've looked at some of these alternative markers. Again, here's the log concentrations of this range that these are alternative types of the virome of wastewater that are there. Are they at levels that are above what would be necessary to measure? And it's weird here. If you look at this organism, this is called PMLV. This is the pepper mild mottle virus. This is a virus that infects pepper plants. And it is at the highest concentration of black water and in gray water, pretty much, other than this G23 is another one of the viruses that are naturally in wastewater. Not human associated with, not pathogen, but at high levels. So maybe these are alternative markers to look at. Now, why would pepper mild mottle, what's that?
Water from New Mexico, maybe?
No, this was, we've seen the same thing. This data here specifically is from San Francisco. But we also saw the same thing in water we collected in Cincinnati. So
You guys look it up for-
we have not done that yet. Again, because for the non-potable.
Repeat the questions for me.
Oh, sorry. The the question was about where is the water from. I think that was probably evident from my answer. But we do not look at pharmaceuticals because for non-potable reuse, the exposure there is not of concern. It's more the acute risk from disease organisms. All right. So anyway, just summarize here. We developed these log reduction targets that I mentioned. They're in the guidebook for, we published the work, but then they've also been translated as guidebook for developing and implementing regulations for on-site non-potable water systems. And that is now being used by different states for legislation on this area. And we're doing continuing improvement of the QMRA models, looking at initial pathogen data, measurements and models, like I mentioned, looking at log reduction credits. And then we're also looking at these more effective biological targets for monitoring performance and developing associated standard methods. And I'm going to skip this because we don't have time, but I would leave you this. You guys are welcome to have this presentation too. It's not, these data are on the site as well as the Blue Ribbon Commission website and sorry for running a little bit long.
I started you late. Any questions? So
AICAT put on a presentation chemical engineering.
Yeah.
On potable water reuse, looking at 2 systems in Southern California, large scale.
Yeah.
So one of the big detractions that you mentioned at the beginning, purple pipes, the whole bit. But to what extent do these play with each other?
Well, I think the one thing is they're using the same approach. So all the DPR work is using the same risk-based approach where they're modeling log reduction credits. So the log reduction targets that state of California using is 12, 12, 10. 12 for virus, 12 for parasite, 10 for bacteria. That's the log. You have to develop systems that can ensure that you're getting that removal of all those different reference pathogens. And so that's the biggest similarity. The other part of that is where they're going is it's really about monitoring. It's about online monitoring, ensuring that your performance, because the out of spec performance is what's going to drive your risk. So it's about ensuring effective monitoring as well. So there's a lot of similarities there. I think overall about what's the value of doing DPR versus non-potable or potable reuse versus non-potable reuse. I think it depends on what your driver is. If you're in a very water stressed area like Southern California, then maybe they want to go all in. And certainly direct potable reuse seems to make a lot more sense economically than indirect potable reuse. Because that sense where they're doing high levels of treatment, then injecting the water into the aquifer and then pumping it back out. So why have those extra costly stages there? Because you think you're getting some log removal credit for the groundwater treatment. Well, we have the systems now to meet the log removal credits just in an engineered fashion. So it's more about having effective control over that. Now, the biggest difference is what Cheryl mentioned. If you go to potable reuse, then you need to understand the other risk, the chemical risk analysis too. But the data would indicate that it's probably, it's a lot of it's perception, right? I mean, if you look at the pharmaceuticals, the concentrations of those pharmaceuticals are so much lower than the oral doses that people are taking. Now you can argue I'm not taking that, so I don't want to take it. I don't have anything in there. Well, get to what's the acceptable level of risk. And unless there's something we don't really understand very well about cumulative low dose exposures of a variety of these chemicals, then we're probably safe. Now, I think we are safe, but maybe there's more about cumulative low dose exposure that we don't understand.
And Jay, kind of a follow-up question related to that is, has anybody looked at, say, heavy metals from gray water, storm runoff, and things like that, loadings, and how much removal you get with these systems that are designed based on the microbial risk alone?
Right. All right. So the question was about storm waters and chemical contamination there. And it's clearly when you start talking about stormwater collection as opposed to at roof collected versus stormwater collected at grade. I mean that there's a lot more contamination in that water, including a lot of fecal contamination. I kind of breezed over it in my slide, but when we went to look at stormwater, there isn't very good data on pathogen concentration of stormwater. There's decent amount of data on fecal indicators in pathogens, and there's a range. So we modeled stormwater as a 10-fold dilution of sewage or as a 1,000-fold dilution of sewage. Because if you look at the data out there, that's kind of what you see. So number one, it's contaminated, and it's pretty highly contaminated. So you need to incorporate relatively high level of treatment, water reuse, even for non-potable purposes. For the chemical contaminants, it's kind of back to the question Cyril asked. For non-potable reuse, if you're meeting general water quality acceptability, it's turbidity and BOD. I mean, it doesn't smell bad and it doesn't look bad. You're probably fine. Metal contamination things, again, if you're not ingesting it, if you're using it to flush the toilet and other kind of non-potable uses, it's of lower concern. But there could be certain kinds of stormwater that may be very high in certain targeted contaminants, non-bacterial contaminants or non-microbial contaminants that you really would want to probably avoid that stormwater or do some level of sanitary survey of your system. Yep.
One last question here online. Srijan, who's a faculty member at the UAF, asked, what is the suggested frequency for monitoring CR?
I would say not any. I wouldn't advise requiring any more sampling with qPCR than I would with even more typical culture-based techniques. I think the emphasis of this group has been really focus on online parameters as much as possible. Any offline analysis, whether even though it's maybe slightly quicker qPCR than culture-based, you don't have to grow it up for a day or two. Even then, it still tends to be you taking the sample, it's going offline, it's delayed. So whether you're qPCR, whether it's molecular or culture-based, it's probably not either one. I would advise against it. You're only going to use those kind of targeted measurements to look at validation or recommissioning, but not as an online kind of, or not as a continuous performance monitor. And the one thing that comes up with qPCR too is that when you do that, you're detecting the gene that's present. You don't know if the organism is alive, which is a little bit of a complicating factor there. Thank you.
Thank you,
Yeah,
Jay.
Yep.
Thanks, Jay.
In total, we had about 18 online.
Good one. I wish I would have.
Enjoy Alaska.
So one of the reasons I'm asking some of the questions that I was asking, I work with folks that have been quantifying things like Lipitor and Prozac in dolphins off the coast of North Carolina.
Yeah.
And also the toxic issue in sea otters. And of course, these are animals that are stuck in the water that are discharged from city areas.
Yeah.
It's not like they're just flushing a toilet with it.
Well, no, but I should have said. I mean, I think the ecological exposures are much of greater concern for those kind of chemicals than the human exposure, because by the time you get through the treatment system for DPR use, it's gone through RO, it's gone through a range of filtrations, including usually RO, and then some advanced oxidation. So it's not as contaminated as the wastewater those dolphins are swimming in, or the surface waters.